Okay, so this is section 7.1, integrals as net change. And what we're looking at is how we can use the integral and the value of the integral to explain physical quantities. And so we're going to start out by talking about a honeybee making several trips from the hive to a flower. So the honeybee's velocity is as shown. So the honeybee starts at the hive here and is going to fly to the flower. So that part of the velocity graph represents the honeybee flying from hive to flower. And so as we let the honeybee fly, this integration of that piecewise function using the area model, that is a value of 200. And so this would represent then that distance traveled from the hive to the flower. So the honeybee is going to collect some pollen, and then the honeybee is going to fly back to the hive, which is represented by this on the graph, and deposit the pollen in the hive, and then the honeybee is going to go back to the flower again, get more pollen, and then fly back to the hive. But in this case, I have the honeybee not making it all the way back to the hive, but stopping short of the hive. So one physical quantity we can use the value of the integral to find is the total distance traveled. So total distance traveled by the honeybee is treating each one of these regions as positive. And so when we do that, then we get a total value of 700 feet. So if we think of the honeybee flying 200, then 400, then 600, then 700. So it's that total distance traveled is like reading your odometer on your car. The other physical quantity we can talk about is the displacement of the bee. So as we can kind of think of this as our negative area model strategy. So if we look at the same graph and acknowledge the fact that really the value of the integral for functions that fall below the horizontal axis is negative, then the displacement ends up being adding the values of all of these integrals, and so the resulting displacement is 100 feet, and this bee is flying back towards the hive. So this physical quantity of displacement is the actual values of the integration. So, so that gives us our two physical quantities that we can determine using integration. Displacement is our net change. So if we were to annotate what we're reading here, net change, pretty important piece of information to underline. And here, this last sentence, treating regions as positive or negative. So our displacement is the physical value of the integral, whereas the distance traveled is treating all regions as positive in value. So we can accomplish that algebraically by integrating an absolute value function. In other words, making all regions positive. Today we're also going to go back and work with finding total area analytically. So this comes out of section 5.4. I just wanted to bring this this tiny anchor chart, I guess you could call it, back into the picture here. We'll be using that also today. So our next example here, we're going to look at having a velocity graph and creating the position graph. So we know that the physical quantity when we integrate a velocity graph, we get our displacement. So using our area model here, the value for this region is 1 by 1, so the value for that region is 1. The value for this region is a half, but for some reason it's not animating in the right order. The 1/2 will pop up here. The value for this region is actually negative a half, and the value for this region is 2. So when we're talking about the displacement, we're talking about taking the actual values for each one of the regions. So it's 1 plus a half, 1 plus a half, minus a half, minus 2, so our displacement is negative 1. In other words, from where we start, we end up 1 backwards from where we started. Our distance traveled, we're going to treat all of the regions as positives. So taking the absolute value of all of these, we get a total distance traveled of 4. So how we can make that look in our position graph is, let's say we start with an initial position of 0. This 1 here represents a displacement of 1 meter, meaning we move up 1 on the position graph. So after a second, we're at 1. Since this is a constant function, this has got to be a linear relationship. We're going to increase that power on the function by 1. This next piece, that means we're going to have a displacement of a half. I knew it would pop up eventually. So that means if at 1 second we're here, then at 2 seconds we're up a half. So we're about right here. And this curve is what goes between 1 and 2. This being linear, this has got to be a quadratic function when we do the antiderivative. And then we have a region beneath the y-axis. So it's going to result in a negative displacement. So we're going to go down a half a meter, and then we're going to have a negative displacement of 2 from that point. And that's going to take us all the way to 5 seconds. And we're going to end up with a displacement of negative 2. That's what this 2 represents. And we're going to end up down here as our final position. So if we notice our initial position was 0, our final position is negative 1. That's where this negative 1 comes from. And if we add up all of the absolute values of these, we can see that the absolute values all equal 4. A lot of AP exams I've seen have at least one of these drawing the position from the velocity graph. So we'll kind of keep our eye out for that. And it's usually geometric shapes, nothing more difficult than some geometry. So with that in mind, we're going to continue with this area model here. And it says we have a particle moving, and its velocity relationship is the graph given. And the particle starts at x equals 2. So the initial position is 2. So we're going to have to figure out how to incorporate that into our solutions here. So it says find where the particle is at the end of the trip. So in other words, at the end of the trip, it's our final position. We're going to have to factor in some displacement here. So if our x initial is 2, and our displacement represents our net change or our movement, then let's go ahead and use the area model here and figure out how much we've moved. So in the first 2 seconds, and our displacement is represented by the actual integral. We're going to use over here, we're going to use this graph as the workspace. So 1/2 base times height here is 1/2 2 times 5, which is 5. And here I see a trapezoid, but I also see triangle, rectangle, triangle. So for this region here, let's see, this is 1 by 5, so this is 2.5. This is 1 by 5, so it's another 2.5. So together the two ended triangles are 5. And then the middle is 1, 2, 3 by 5. So the middle is 15. So we've got 20 here, 5 plus 15, all beneath the axis, so that's negative 20. And then this is also a triangle, 1/2 base times height. So we have a height of 5, base of 3, it's 15, a half of that is 7.5. So our net change then, which we can represent using the integral notation, is going to be adding up all of these values. So we've got 5 plus negative 20 plus 7.5, and that is negative 7.5. So if you think about starting at 2 and moving to the left 7.5, or moving a negative 7.5, our final position is going to be our initial position plus our displacement. And so it's negative 7.5 plus 2, so our final position must be negative 5.5. Now let's look at the total distance traveled by the particle. So we can treat each one of these regions as positive. And so we have 5 plus 20 plus 7.5. So our total distance traveled is 32.5. meters. That's like our odometer reading. Notice to answer the total distance traveled question, you don't need an initial position. It's just asking for how much you've moved altogether. Let's talk a little bit about the units right now, because it's really common to ask about units in questions like this. We can find units the same way we find area, by multiplication. So our units are always going to be found by multiplying our vertical axis units by our horizontal axis units. So we're going to have meters per second times seconds. So the y units, meters per second, the x units, seconds. Our seconds are going to cancel. And so our area then must be measured in meters, which is why we have the unit of meters on each one of these values. Example 4 here requires a graphing calculator. We have a particle that's traveling with a velocity of t minus 2 times sine t for 5 seconds. So if we graph that on our graphing calculator, it looks like this over the first 5 seconds. 1, 2, 3, 4, 5. And we can kind of see that oscillation we get when we have a sine function. It just doesn't look nice and symmetrical because of this portion of the function. So we want to know then the particle's displacement. And I'm asking you to set up but do not solve. It's really common to ask a question like this where they're just looking for your notation with your integration symbols. They don't really care about you integrating it. In fact, you can't integrate this with what you know about in Calculus AB. So we know that displacement is the integral of velocity. So we're going to set up an integral symbol. And so when we're grading these setups here, what the grader is looking for is 3 things. They're looking for your integral symbol and your dt. Those two together are worth a single point. Missing either one of those, it will forfeit the point. It's also looking for upper and lower bounds. So we're going to start at 0, and we're going to go to 5. So that's another point. And then the third point is putting the function into the integrand location. So I'm going to put the t minus 2 times sine t in the integrand position. So this is a 3-point problem. Point for the upper and lower bounds, a point for the integral symbol in the dummy variable dt, and a point for the function. And so that's an expression that will give you the value for the displacement of the particle. Now, if we look at these regions, because since we're talking about displacement, we have to take the actual value of the regions. This region is below the y-axis, so it's negative. This region is above the y-axis, just slightly. It's positive. This region is below the y-axis, so it's negative. So you might guess if we did an f int here, we'd end up with a negative number. We have a much larger negative region overall than a positive region. And so if we do an f int here, and make sure you're in radian mode because of the trig function, then your answer would be negative 3.810. So that would be the displacement. And then if you look up here at the units, we have meters per second times seconds. So we know that the units is meters. And this represents displacement. And so going on then, let's set up and do not solve for the particle's distance traveled. There are 2 expressions that would yield full points here. So we're going to go we know that the distance traveled is the absolute value of this. So we're going to set up both of these. Either one would give you the points for a correct solution. So first we're going to use the absolute value. And the first thing we can do is just go across the entire interval from 0 to 5 and put everything in the absolute value. So that's the first setup that would yield full points. The second setup would be getting 3 integral expressions, one that represent each one of these regions, which means we need to know this and this 0. That's where the functions are equal to 0. Those are the roots. And so in order to find those, we take this function and set it equal to 0. And when we do that, we'll get this location, and this location. So when we set that equal to 0, we know that we have a product of t minus 2 and sine t. So either t minus 2 is 0 or sine t is 0. When we solve this first one, we get t equal to 2. That's this location here. When we solve the sine t equals 0, we're going to get either 0 pi or 2 pi. So if we come back here and look at our domain, 0 is the beginning, pi must be this point right here, and 2 pi is outside the domain. It's somewhere out here. So, so we're not going to include 2 pi as part of our solution. So these values, these roots to the function are going to give us our upper and lower bounds. So we're going to start by writing the integral for this first region. So we're going to have that integral then from 0 to 2. And since this region is negative, we're going to need to use our absolute values. And then to that, we're going to add, when we use the absolute values, it's like considering this region to be up here instead of down here. Then we're going to add to that the next region. And this one goes from 2 to pi. And we don't need the absolute values here because this region's already above the y-axis. So far we've got 1.091 for this, and this one has a value of 0.232. And then the last region here, we're going to need an absolute value sign. It goes from pi to 5. And we're going to use our absolute value signs here. And we use our absolute value, we'll get a value of 2.952. So this green region represents the total distance traveled. And when we add up those three numbers, we get a value of 4.275 meters for the total distance traveled. The same approach can be used for real-life problems, application problems. This problem here is about potato consumption. So while we can integrate velocity to get us position, we can integrate the rate, any rate, to get us an accumulated value. So for instance, integrating velocity, which is the rate of displacement, gets us displacement. Integrating the rate of consumption, in other words, how quickly people consume potatoes, integrating that accumulates and gives us how many potatoes are consumed. So if we look at the potato consumption starting in 1970, then we can say that the amount consumed, if this is the rate, this is the number of millions of potatoes per year. So we know it's a rate because of the word per. So if we take this rate times time, we're going to get millions of bushels, looking at the units. So we're going to model this function, and then we're going to integrate it over the time interval that we're concerned about. And so we're going to go from the beginning of 1972 to the end of 1973. So this function is written, this t for time represents the time from the beginning, in other words, when the model was established, and then going through the years after that. So when we look at the function here, what we're really looking at is this location here, t equals 0 is really 1970. That's when the model was established. And then the next tick mark over is a year later, and so on and so forth. So if this is 1970, then you can picture 12 little tick marks here for January, February, March, April, May, June, July, August, September, October, November, December. And then January's tick mark is 1971. So we're going to go from the beginning of 72, which is right here, that's January of 72, to the end of 73. That means December of 73. So this tick mark is January of 73. So right here would be January of 74. So we have to go to this location. That would be the end of December in 1973. So we're really looking at a 2-year time period. And so we're going to set up an integration then. If this is 0, we're going to start at 1 tick mark 2. So our lower bound is going to be 2, and our upper bound is going to be 4. So this is the region that we're concerned about accumulating and finding the area of. This region is going to give us then the number of millions of bushels of potato we ate in that 2-year period. So we're going to integrate this, and we could integrate this by hand if you remember that e to the x, the different bases, and how we differentiated that. If you don't worry about it. This is a calculator question. So we're going to find the value of this region doing an fint. And when you do an fint on this function, you'll get 7.066. And what you have to remember is that this was measured in millions of bushels per year. So that 7.066 means 7.066 million bushels. So 7,066,000 bushels of potatoes over that 2-year period. So just to kind of quickly recap then, using the integration capabilities as a net change, and answering the questions, how do integrals explain physical quantities? We know that integration represents an accumulation of a rate. And for motion, integrating velocity represents displacement, which is measured in meters or feet. Units become important, and you need to remember to multiply the units on the axes to get that final unit for the integration. So at this point, you can go ahead and do 7.1 homework. It is only a 1-day assignment, so if you feel like you want to take the proficiency quiz instead of doing the homework, you can go ahead and do that in Blackboard.